Welcome to this movie which I have made for my course on classical mechanics. I'm Jos Thijssen and my course is taught to second-year students applied physics at the Technical University of Delft. In this movie I want to start from the Lagrange equations, which I have described in another movie, and I want to explain how you can recast those equations into a new form, and that will introduce the Hamiltonian, and the entire formalism that I will consider in this movie is called the Hamilton formalism. So I hope that this movie is useful to you. So I would like to start by reviewing the Lagrange formalism, and in particular the Lagrange equations of motion. They are formulated in terms of generalized coordinates, and those are the coordinates that we use to describe systems that may be subject to constraints, and they correspond to the degrees of freedom, so each degree of freedom has its own generalized coordinate. The Lagrangian is a function which is defined as the kinetic energy minus the potential energy, so T stands for the kinetic energy and V stands for the potential energy, and this function can be expressed in terms of the Qj dot. The Qj dots derive from the kinetic energy and the Qj's, and there is finally a time dependence. And for this Lagrangian we can write up the Lagrange equations of motion, which read d dt dl dq dot j is dl dqj. And realizing that L is a function of the Qj dots, then obviously the derivative of L with respect to Qj dot may still be a function of the Qj dots. We take then a derivative with respect to the time. Qj dot is a time derivative, and so it is clear then that this is a second order differential equation, or it is a set of second order differential equations in time, and that means that the highest order of the derivative with respect to the time is the second derivative. And of course that should be the case because Newton's equations are second order in the time, and the Lagrange equations are just a reformulation of Newton's equations. From your course on differential equations, you may recall that it's always possible to rewrite a second order differential equation as two first order differential equations, and that's precisely what we will try to do now. And we do that by introducing a new coordinate, and that's pj, and pj is just the object we take the time derivative of, so it's dl dqj, and we call this the momentum. Sometimes people call it the conjugate momentum. It's the momentum which is conjugated to this generalized variable Qj. And we can look at we can consider an example. So if we have a particle, point particle, in 3 dimensions, then we know that the Lagrangian is the sum, it's a half m r dot squared minus v of r. So the generalized coordinates are now just the x, y and z components of the particle, and if I consider the px, for example, that would be dl dx dot. Now we realize that this is x dot squared plus y dot squared plus z dot squared, and we see that this is m x dot, and similar for the y and z components. And so in general we can write that p is m times r dot. and that's indeed recognized as the mechanical momentum of a point particle. However, if we really have constraints and we have different types of generalized coordinates, then Pj will also have a different form. And so it is this generalization of the concept of momentum that we all know from ordinary mechanics of point particles. Back to the definition of the Pj, which is dl dq dot j. This here, the dl dq dot j, occurs in the Lagrange equation of motion. So if we replace it by Pj, we get the following equation. We obtain dPj dt is dl dqj. And now we realize that this equation only contains first order time derivatives of Pj and Qj, and the same holds for this. So we have indeed achieved the goal to replace the second order differential equation, which is the Lagrange equation of motion, which we had over there, by two first order differential equations. Equation number 1, which is the definition of the momentum, and equation number 2, which is the time evolution of the momentum. However, we have introduced a third variable in addition to the Qj and the Qj dot, and that's P. And so there is some redundancy somehow in the problem, because we could either do away with the Pj and then go back to the original Lagrange equation, but we also may use this equation to eliminate Q dot j from the problem and express it in terms of Qj and Pj, and that is an interesting move. So let me go back to this definition of the Pj, which was the derivative of L with respect to Qj dot. And we know that the L depends on all the Qjk dot, and on the Qks, and perhaps also on time. So the idea is these are, if we have k generalized coordinates, so if j and k run from 1 up to capital K, then these are k equations, because we have one equation for each j, and these are all the qk. And now the idea is perhaps we can invert this equation and write q dot j as a function of the pk and the qk. So somehow we would like to eliminate finally the q dot by writing it as a function of the pk and the qk, and we can use this equation to achieve that goal. And the simple example is the following. So here this is the qj dot, and this is the pj, and we see that this goal to write the qj dot in terms of the pk and the qk is in this case obtained rather trivially, because we can write r dot is p over m. So this may be a complicated task generally to find these qj dots as a function of the pk and the qk, but often it turns out to be quite simple, and in particular for a point particle in 3 dimensions we see that we can write the r dot, which is the qj dot, simply in terms of the p's by writing r dot as p over m, and nobody will be surprised by that. So using this result we can throw all the qj dots out of the problem, and we can formulate everything in terms of momenta and positions. And the question now is, can we find a functional, some object which depends on the pk and the qk such that we can derive from that object a kind of equations like the Lagrange equations of motion. And it turns out that that is the case, and that new object is called the Hamiltonian. It's H, and it's defined as follows. It's the sum over J, then we have the Qj dot Pj minus L, which, as we know, depends on the Qj dot and the Qj, and perhaps explicitly on time, if there is an external influence on the system. And now we would like to write this as a function of the Pj and the Qj. And that may seem surprising, because here we have a Qj dot and here we have a Qj dot. But if we would replace this Qj dot each time when it occurs here by this expression in terms of the pk and the qk, for example r dot is p over m, then it's possible to write this h as a function of the pj and the qj. Okay, so h is a function of the momenta and the positions, and there may be, in the case of an influence from outside, still an explicit time dependence. Now it turns out interesting and useful to consider the derivative of this function with respect to the coordinates pj and qj. Well, here I have taken the derivative with respect to qk, because there is a sum over j here. When I take the derivative with respect to qk, that may pick out one element of that sum. But in this case, the q dot j, that was written as a function of all the pk and the qk. So I obtain a sum over j, and then a d q dot j dqk, and then there is a pj. I don't get a contribution from the pj, because the pj and the qj are considered to be independent variables. And we should be careful with L. So first I get a derivative of L with respect to the qk. But there is also a dependence through this qj dot, because the qj dot is a function of the qk and the pk, and so using the chain rule, this gives me a sum over j, and then I have a dl dqj dot, and I must multiply by qj dot derivative with respect to qk. And now we know the following. This dl dqj dot, by definition, that is equal, the L dqj dot is equal to the pj. So this is pj. But we also see a pj here, and both are multiplied by dqj dot qk. This term has a minus sign, this one hasn't, so we can cancel these terms against each other, and this gives me as a final result minus dl dqk, and we know that was the rewriting of the Lagrange equation, that dl dqj is the derivative, the time derivative of pj. So in this case we obtain the time derivative of pk, because we take the derivative with respect to qk. So that's the first result that we obtain. dh, taking derivative with respect to qk, gives me the pk dot. So, in view of that result, let's now consider the dh dpk. And for this I get two contributions. The first one is a sum over j. This is analogous to what we had before. We have a dq dot j dpk multiplied by pj, but there is obviously also a contribution from this pj. So we also have, when the j hits the value k here, then we have a q dot k. Then we consider the Lagrangian. The qj is independent of pj, so that doesn't give a contribution when we take derivative with respect to the pj, but this one does, and it gives me a sum over j dl dqj dot, and then we have dqj dot dpk. And again, just like in the previous line, we can identify this with pj, and then we see that again this term cancels against this term, and so we are left with q dot k. And so let me then finally put these equations together. I see that p dot k is minus dh dqk, and we have qk dot equals dh dpk, and these two equations are known as Hamilton's equations of motion. And they are very important. They are first order differential equations, and that means that if I know the initial value of the pk and the qk, or the pj and the qj, which is basically the same, then these equations give me a unique time evolution. So in the space of p's and q's, when I have a particular point, that point will evolve in time, and that's governed by the Hamiltonian. So the Hamiltonian gives me the time evolution of the points in the space of all the momenta and positions, or all this, let's say, the generalized coordinates and their associate momenta. Finally, let's go back to the Hamiltonian, which was defined in this way, and which is a function of the independent coordinates pj, qj, and the time. And I'm interested now in the time evolution of that Hamiltonian. So how does it change in time? And now it turns out we can calculate this obviously in this way. This is h is a function of the pj, so I use the chain rule. I first get the derivative with respect to the pj times the time derivatives of the pj's, and the similar for the dq. And then I have also this explicit time dependence, so remember that was this last dependence here, which was eventually there and which is always due to some external influence, and this is the result for the dh dt. Now I see that this equation contains p dot j and the q dot j, and so I can use these equations in order to rewrite that equation in a slightly different form. So I have a dh dpj, and the pj dot is the minus of dh dqj. So in this case I do not use the p dot k, but I use the p dot j. And then I have a second term, and that second term is dh dqj, and the q dot j is dh dpj. And then I may have this explicit time dependence. Now you immediately see that this term is the same as that term, but it has a minus sign. So the first two terms here, the first two sums, they cancel, and therefore I'm left with only a dh dt. So in principle the Hamiltonian is constant in time unless there is an explicit time dependence, and the explicit time dependence, it can only be due to an external force which we apply to the system, and that external force should also be time dependent. I would like to conclude this movie by considering this rather common case of a system which has constraints that are time independent, and there's also a time independent potential. And so that means that L is t minus v, v is independent of time, and t is given in terms of the original coordinates of the point particles as mi over 2 times the velocity of those particles squared. Now, if there are constraints, then the positions of the point particles Ri can be parametrized via the generalized coordinates, and thus in this case, because of these properties of the system, there is no explicit time dependence. Well, if we have that and we want to calculate the velocity, we can do that easily using the chain rule. We take the derivative of Ri with respect to Qj, and then we multiply by the Qj dot. And so that's what we are going to put into the expression for the kinetic energy back again. And that gives me a sum over I. Then there is a sum over j. Those are the generalized coordinates, and k, because we have an Ri squared, so we get two sums. There is an mi over 2. And there is a dri dqj, and there is a dri dqk. And then we should multiply by qj dot and qk dot. And so we can write this in the form half, and then sum over j and k, m, capital M, j, k, qj dot, qk. Well, we have lumped quite some terms into this m, so let me specify what mjk is. It's a sum over I of mi times dri dqj dri dqk. So this is a rather generic form of the kinetic energy. It occurs quite often, so in systems that do not have the time dependencies either imposed in the constraints or in the forces. And if we have this particular form of the kinetic energy, then it's rather easy to calculate the momenta. So the pj in this case, by definition it's dl dq dot k, or the dq dot j, but as the potential does not depend on the velocities, the Lagrangian assumes always that we have a conservative system, The only contribution to this derivative can come from the kinetic energy. So we have a dt dq dot j, and it gives me a sum over k m gk jk, and then a q dot k. Now you might be surprised, because here there was a half, so where has the half gone? Well, it turns out this is a sum over j and it's a sum over k, and so we get a contribution to this which is due to the first q dot j, and we have a contribution from the q dot k. And because we can see from this expression, by swapping these two terms, that mjk is mkj, that's symmetric, that these two contributions are exactly the same. And if we have two contributions and a factor of a half in front, there is only one left. So that is the pj. And having that pj, we can calculate the h. The h was defined as a sum over j, and then we have a pj times q dot to the j minus a t plus v. So what I have now written here as t plus v is obviously minus L. And so we can evaluate this, because we have here the expression for the pj, that is a sum over k mj k q dot j q dot k. The kinetic energy was written in this form here, so that's again a sum over j and over k with a half in front of it, and then we have mj k q dot j q dot k, and we have plus the v, which only depends on all the coordinates qj or qk. And now we see that the first two terms are equal up to this factor of half and the minus sign, so I'm left with only a half times mjk q dot jqk, and that is precisely t plus v, and we recognize this as the mechanical energy. So what we have shown is that under the conditions for this particular system, that the constraints and the forces are time independent, we can conclude that whereas the Lagrangian is t minus v, the Hamiltonian is always t plus v, and that's the mechanical energy. Now if we connect that to the conclusion here for the time derivative of the Hamiltonian, there are no external forces in the case we just described, and so we have proven now again that the energy of the system, the mechanical energy, is conserved.